So let's continue with 9.3, and the good news is we've built up our collection of identities now. We're not going to be adding any new identities to this collection. We're just going to work with what we have, and we are going to focus on the double angle identities for a few problems. So here I just want to refer back to our identity sheet. The focus on the next few exercises is going to be problems that involve these identities of double angle identities, sine 2 theta, cosine 2 theta. We won't have to use tan 2 theta in any of our exercises, just sine and cosine. And so let's take a look at a problem here. Find the exact values of sine 2x, cosine 2x, tan 2x, if we know the following. Sine x is 3/5 and x is in quadrant 2. And so why are we using double angle identities here? Where's the 2 theta? Well, of course, we don't have to use theta as our variable in each case. Here, the x is just like a theta. So the fact that we want to find sine 2x, cosine 2x, tan 2x is kind of a signal here that we're going to use our double angle identity to help us out. And what we're given is we know a value for sine. We know sine of x itself is 3/5. And we also know x is in quadrant 2. So we may have to make use of that quadrant information along the way. So I want to find sine 2x. When I think of that double angle identity, sine 2 theta, you can say I can get sine of 2 times an angle if I know sine of the angle and cosine of the angle. I can plug in the sine and cosine of theta on the right, figure out the right-hand side, and that's going to tell me the sine of 2 times theta. So what we're seeing here is to use sine of 2 theta equals 2 sine theta cosine theta, our double angle identity. We need cosine x. I'm going to call it cosine x here because the angle we're working with is called x in this problem. So to use that double angle identity, we need cosine x. We have the sine, and we want to find cosine. Now, we have gone through that process many, many times, and I'm actually going to introduce a second approach to that in the next couple of problems. And yet, I want to look at it both ways. So I'm going to call this 2 methods. Method 1 is using the Pythagorean identity. And then we're going to look at a different way that might help some of us in problems where the calculations get really, really messy. But first, let's just use the Pythagorean identity. So we're going to use, I'm going to write it as sine squared x plus cosine squared x equals 1 because my given sine x is written as sine x, right? I'm going to plug in that 3/5. So 3/5 squared plus cosine x squared is 1. And here we go again. Cosine x squared is 1 minus, when I square 3/5, I get 9/25. Cosine x squared is going to be 25/25 minus 9/25 is 16/25. And now I can take square roots. So cosine x is plus or minus the square root of 16/25. And every once in a while, we get a problem where we can actually simplify the square roots completely. And here we can. And also, now I'm going to make use of the quadrant information. Because we're in quadrant 2, I know that my cosine actually has to be negative, right, in quadrant 2. Sine is positive, but cosine is negative in quadrant 2. When I take square roots, I get 4/5. So I'm just going to write here in red, quadrant 2, we're invoking here to be able to make that sign choice. All right? So there, we were able to get cosine and what I want to do is I want to jump to a second method for finding cosine. So we're going to do the same thing before we even finish the problem, because I want to be able to compare these next to each other. It's using using a reference triangle. And relying on SOHCAHTOA. Okay. So remember, this is to find cosine theta. So we know, well, first of all, before I fill in what we know, I just want to say we're going to work with the right triangle. Draw my right triangle right here. And the right triangle that we're working with, I'm going to say, has the reference angle for x as one of its acute angles. I'm not calling this x itself because x is in quadrant 2. That's part of the given information. So x is not an acute angle. We cannot draw a right triangle with the angle x as an acute angle, but we can draw a right triangle with the reference angle for x. And remember, the reference angle has almost the same sine and cosine. The reference angle will have a positive sine and cosine. X's sine and cosine in different situations could possibly be negative, but it'll either be equal to the reference angle value or minus the reference angle value. So, all right, we know sine of x is 3/5, so sine of the reference angle is also 3/5. And I can label this triangle now using SOHCAHTOA. I'm going to think of opposite over the hypotenuse when I use that 3/5. Now I'm making up the triangle, so I get to choose the lengths of these sides. And I'm starting from scratch. So opposite the reference angle is 3. The hypotenuse is 5. This adjacent side, maybe I'll just call it A for adjacent, we can solve for using the Pythagorean theorem, right? We know a squared plus 3 squared is 5 squared. A squared plus 9 is 25. A squared is going to be 25 minus 9 is 16. A is the square root of 16, or 4. So we know our value of A must be 4. It's not too hard to figure out from this Pythagorean theorem calculation. Okay. Well, now it's easy from the triangle to write down cosine of the reference angle. Cosine of the reference angle is going to be adjacent over hypotenuse. That's our SOHCAHTOA relationship there. And the adjacent side is 4. The hypotenuse is 5. For the reference angle, that's positive. Okay. But now we can use that to get cosine of x. And here's where we got to remember that x is quadrant 2. So that helps us decide whether to use plus or minus this value of 4/5. Well, quadrant 2, cosine is negative, so we use negative 4/5. And so we have the same result here. And in fact, we kind of did the same calculation in method 1 and method 2, we could either rely on the Pythagorean identity, sine squared x plus cosine squared x equals 1, or we could draw a right triangle and use SOHCAHTOA. But if we rely on the right triangle, we call that a reference triangle, because it's the reference angle for x that occurs as an acute angle. And that's fine. We just have to realize the values we get will be positive from the reference angle, and we have to decide whether to use a plus or minus of certain values when we're trying to find actual sines and cosines. Okay? All right, now, so that was the second method for finding cosine of 4/5. I won't force you to use one or the other. You can choose. And now we got to finish our problem, right? We got to find sine of 2x is one thing, which now we can just plug into that identity, because sine 2x is 2 sine x cosine x. I'm just copying down my double angle identity for sine, which that one comes in only one form, one version, and I wrote x's because x is the input here that were in our problem, and now I'm going to plug in my values. 2 times sine x is, that was given right at the beginning, 3/5. We didn't have to figure that out. And cosine is negative 4/5. So now I got to multiply across. That 2 is like 2 over 1. So it looks like I got 6 times 4, 24. Negative 24 25ths is my value of sine 2x. Cosine 2x. Now when you calculate cosine of a double angle, you got a choice. You can use any one of the 3 forms of the right-hand side. They'll all give you the same thing. I'm just going to pick the first form here, cosine squared. I want to write x minus sine squared x. So to use that formula here, I'm going to take my cosine value, negative 4/5, and square it, minus the sine value, 3/5, and square it. And I think I can fit this on here. We're going to have positive 16 25ths minus 9 25ths. 16 minus 9 is that, looks like 7 25ths from that identity. Okay. And can I squeeze it onto this piece of paper here? We also want tangent 2 theta, or tangent 2x. And for most cases, when I want a tangent, I'm just going to use my values for sine and cosine. So I can just take my sine 2x over cosine 2x, and that's going to be negative 24 25ths over 7 25ths. I have to carry out that fraction division. The 25 is going to cancel when I divide, and I end up with negative 24 sevenths. I get a negative value for tangent. That makes sense because I'm in quadrant 2. Tangent should be negative. So here is my are my values for sine of 2x, cosine of 2x, tangent of 2x. And let's see if I can back out a bit and maybe get the whole sheet in a shot. And we're going to stop there, and we're going to do another problem. The next problem is going to be a little bit more intense.